In our second lecture for week 2 of weather, we're going to face the most challenging subject of atmospheric stability. I'm just going to be honest with you. You really need to pay attention to understand this. There's a lot of the things that we've been talking about so far, high pressure, low pressure, and how they all work together, and air masses that move across. We're mostly concerned with the United States. So first of all, we need to realize that atmospheric pressure is also a player in wind, moisture, the temperature, all of these things. It's all a reaction. Remember, I talked about how everything's a reaction to the sun and the responses of the earth in different places in different parts. So atmospheric stability is defined as the resistance of the atmosphere to vertical motion. Okay, so that's very important that you understand that. Vertical motion. Unstable air, we have vertical motion. Stable air, we don't have vertical motion, but we can have horizontal motion of air. So the first thing we got to understand is the fact that air has a weight. Atmospheric pressure, air weighs about 14.7 pounds per square inch. And so, the further you get above the earth, the less pressure there is, because that air weighs 14.7 pounds per square inch. So this is equal to 29.92 inch columns of mercury and is considered the normal or standard atmospheric pressure at sea level. Okay? So that's very important to understand. So atmospheric pressure is going to vary with elevation above the Earth's surface. As we go higher, there's going to be less pressure, right? The higher the elevation, the lower the atmospheric pressure. So there's a lot of factors that are going to affect the movement of air mass. Now, it's important you catch all of these. First of all, the Earth's rotation. Where do storms usually go in the West Coast? They go to the East Coast, okay? They come to us off of the Pacific Ocean or down from Alaska, and they go east. And that's mostly because of the Earth's rotation, but it's also from prevailing winds. So changes in temperature and in pressure are going to have an effect on air stability, atmospheric stability. Wind is caused when a high pressure area moves toward an area of low pressure, and we talked about that when we talked about wind, that wind goes from high pressure to low pressure. The vertical movement of air now is going to be controlled by the stability of the atmosphere. And that's going to depend. It's going to have an enormous effect on our fires, but depending on the stability of the atmosphere, air can either rise, sink, or just lay there, like fog, right? It just remains the same. So stable air resists vertical movement. Our photograph in the background, that's unstable air. There's vertical movement, and we can see that not only caused by the fire, but the kind of day it is with the temperature. So unstable air heat is going to rise freely. In stable air, we have very little vertical movement. We only have horizontal movement. So a big player in this is lapse rate. We need to understand also called adiabatic lapse rate. And it's defined as the change in temperature caused by change in altitude. So when we go up in altitude, what happens? Does it get hotter or does it get colder? Well, I'm sure you guys all know it gets colder. So the basic dry lapse rate is 5.5 degrees per 1,000 feet of elevation. The moist lapse rate is about 3 degrees per 1,000 feet of elevation. So I always like to watch the temperature gauge when I go up to the mountains and see it dropping rapidly, especially as I get up into those where I'm going up, quite quickly in elevation. It gets cooler. The back way to Big Bear is a great example of that. You go from the desert to the mountains in a very short period of time, and you can just see the temperature dropping if you have a thermometer. So the average lapse rate between the moist and the dry is about 3.5 degrees per 1,000 feet of elevation change. Now that is significant, and once the atmosphere reaches saturation, dew point, the moist lapse rate is going to control your cooling. Okay? So, the movement of air is an attempt by the atmosphere to gain balance. We talked about that in the first lecture about the Earth wanting to have balance, and it's constantly seeking it, and that causes our air masses to move around. And part of this balancing act is the vertical movement of air masses. So if things are in balance, there's little vertical movement of air, and we call that stable air. But if things are not in balance, the air is considered unstable, and there is more vertical movement. Now, since hot air rises, when the sun rises and the air is heated and the earth is heated, the earth absorbs it and gives it off. And if a mass of air starts to get heated, it's going to start to rise. Now, that has an effect on our winds that we talked about, but it also is going to have an effect on air stability. It's going to reach a level where the surrounding air is of the same temperature, and that hot air is going to go up until it reaches that surrounding air where it's the same temperature. Now, as it goes up, it expands, and it gets the hot air expands and gets bigger in size and takes up more space. So we talk about in the lapse rate, and inversions and stuff. So when we have neutral air in between the stable and the unstable air, so as the air is heating up, it's going up. Let's look at the next one. I think that chart is a little confusing for some. So lapse rate indicators are as follow. If the temperature decrease is greater than 5.5 per 1,000 feet, the air is unstable, and there's going to be vertical movement of air. If the temperature decrease is less than 5.5 per 1,000 feet, the air is stable, and there is not going to be a lot of vertical movement of air. So if the temperature decrease is 5.5 per 1,000 feet, the air is neutral, and there's going to be very, very little movement of air. So we need to realize that now the stable air resists vertical movement, and if an air mass is forced to lift as it goes over a mountain range, it's going to tend to settle back to that original level on the other side, because that's where it wants to be, because it's stable. If the atmosphere is unstable, any air mass that is lifted will tend to rise until its temperature decreases. And so we see a lot of hot air masses that go up against the mountains, and then they keep going, and we get these kind of cumulonimbus formations, not pyrocumulus like the one in the picture in the background, but a true cumulonimbus will oftentimes happen on the edge of mountain ranges. So the cooling of the upper air can also cause the atmosphere to become unstable. And the weather changes are going to be driven by the desire of the masses to try and equalize. So here's a great illustration. This one's so much better. So stable air is going to go up and over a mountain and just go right back to where it was. It likes staying at a certain level. And it's going to, that doesn't mean we won't have winds. In fact, some would say a Santa Ana condition is actually stable air because it's horizontal movement, not vertical movement. Now, unstable air, however, we've got tons of vertical movement, and what's going up can also come down too in our downdrafts as the hot air goes up and it expands, and as it cools, it's the moisture is accumulating and it reaches its dew point, and there's too much moisture in it. So you start to see the clouds develop, and that's where we'll start having stratus, and then cumulus, and then cumulus congestus or cumulus castellanus or something of that type, and eventually we'll get a full-blown thunderstorm-looking lightning and all of that kind of stuff, cumulonimbus formation. So unstable air can intensify our fires by increasing the chance of dust devils and fire whirls because of the vertical movement of convective air, the potential for gusty surface winds, the height, strength, and speed of convective columns. And remember, what goes up can cool and come back down, so we get downdrafts too. And we also have many more spot fires. So here's some just little visible indicators. If you have a smoke column that drifts apart after limited rise, it's pretty stable air. Okay, you're going to have poor visibility in lower levels due to accumulation of haze and smoke. So I've been to fires where I love to tell the story. We went to a fire in Newhall, and the air was extremely stable, and it was foggy out, and you couldn't tell the difference between fog and smoke, but you could smell the smoke, and we knew there was a fire. We went to the address. You could barely even see the address. One of the engines got there before us. We were the first squad on scene, paramedic squad, and then our engine was right behind us and showed up. And, paramedics hate this, but a lot of times the incident commander will give the paramedics the job of stand by in case somebody gets hurt. So we didn't get to go fight the fire. So we're just kind of standing by. And I'm telling you, it was such a mixture of smoke and fog, and the air was so stable, the visibility, you could barely see the house from the sidewalk. So we're walking around, and then the smoke is even getting worse, but I decided, let's go see what's going on. And my partner and I walked around the side of this house, and again, really bad visibility, but we could kind of see people walking around, and I saw our engineer, Jerry, and I walked up and says, "What's going on, Jerry?" And he goes, "Nah, nothing." He says, "It's not that big of a deal, but a lot of smoke, and they've got the fire out, and we're kind of cleaning up, and yada, yada." And then while I'm talking to him, my partner's name is Brian, I said to Jerry, I said, "Well, where'd Brian go?" And he goes, "I don't know. He was standing right next to you a second ago." And I said, "Huh. He must have gone back out to the squad." So we're standing there talking still, and I hear this whoosh, whoosh, whoosh kind of sound, and I look over, and Brian is soaking wet. He is drenched from head to toe. He's still got his turnouts on and his breathing apparatus and his helmet, and he's just dripping wet. And I looked at him and I said, "What happened to you?" He said, "I fell in the pool." And I said, "What pool?" And he goes, "The one right behind us." And I turned around, and we were standing on the edge of a pool, and he had backed up when he was going to walk away, and he fell in the pool. And we didn't hear a splash or nothing. and he sunk to the bottom of the pool, and he had to walk out with all that heavy weight on him. He had to just walk out and get into the shallow end, and walked out the steps. So stable air is a good thing in the sense of the fire won't be vicious, but it's a bad thing in that you have really low visibility. Now, however, unstable air is much worse. Upward, and that is a funny story, isn't it? So I hope you don't mind that I took the time to tell that story. Upward and downward currents are going to be very much a part of unstable air. You're going to get cumulonimbus type of clouds that are going to grow vertically. You will have good visibility down at the fire because all the smoke's going straight up, but you're also going to have dust devils, lower and or fire whirls, and lower elevation intense heat. So part of this is the inversion layers. So we have inversion layers where very stable air, where contrary to normal behavior, the temperature rises as the altitude increases, but you have stable air over unstable air, or vice versa, unstable air over stable air. So temperatures in an inversion layer may increase as much as 15 degrees per 1,000 feet in altitude. Sometimes you can get a thermal belt in the valleys, a warm area on a mountain slope, where we have the cool air up above, and we have warm air above it. So we call this an inversion layer. So we got the warm air above the cool air. Now a fire is going to intensify the hot air in that cool air, where it's going to want to go up and then go out. But eventually, if we get a big enough fire, it's going to break through, and like opening up a chimney, it's going to break the inversion layer. And this is really an intense change in the fire underneath that breaking through of the inversion layer. So a strong inversion is when warmer air caps cooler air. If the fire breaks the inversion, we get this draft effect, and everything's going to increase. Now, a nighttime inversion is what happens in Ventura all the time. We have air created when heat is radiated away at night, and off of the ocean, cooler air is coming, and this occurs mainly inland valleys and mountain areas, but also near the ocean, and we get these, then we call that other one a marine inversion. This is a nighttime inversion. So this cooler air settles down, and then it weakens after sunrise when the earth warms up. So stable air versus unstable air. Unstable air has heating from below, and it's going to increase fire behavior. Stable air has cooling from below. So inversions can break down and weaken after sunrise. As the sun rises, the earth heats up and it warms up, and so does the air. And as the air heats up, it goes up, and that's what causes the winds to go up. Winds go up canyon, up mountain, up valley. And so as that happens, then the inversions are usually going to break down somewhere before noon. But, you know, it depends on the day how hot it is. So the more vertical air movement, the greater the fire behavior. So if you're fighting fire in an area where inversion layers are present, you need to be aware and monitor the weather. Pay attention. We're going to talk about that in the last slide. Monitor the weather. How are we going to do that? We need to detect those potential changes in weather. You don't want to be surprised by an event that is very predictable. So winds are going to pick up somewhere between 10 and 12 because of that going on. Now, a marine inversion is what I was talking about in Ventura, where you have cool, moist air coming off of the ocean, and we get oftentimes fog. The thicker the layer, the farther inland it will invade. And this is great. We love the fog most of the time. It brings cool, moist air, but it's generally strongest and most noticeable at night. So fog and stratus clouds are a sign of stable air. If you see stratus clouds, it's pretty stable air, or fog, of course. Now there's subsidence inversion, and this is a slow sinking motion of a high-level air mass over a broad area. And it occurs when the high-pressure system is stationary for several days. That's what we have had here recently, where we have hot air. We've had a high that's over us for a long time, causing intense heat. It was 116 degrees in Santa Clarita yesterday. So when that air mass sinks, it compresses, becomes warmer, and the relative humidity can fall dramatically. So this causes a subsidence inversion, and they can hold smoke in a wide area for days and even weeks. And this happened yesterday and this morning, where we woke up to heavy, smoky, foggy, weird, an orange glow in the sky when I woke up this morning. So that's subsidence inversion. They also can prevent nighttime relative humidity recovery. Now, I mentioned that you can sometimes have a warm belt, and in valleys in the mountains, like in Yosemite or Kings Canyon, you can sometimes get these thermal belts where a nighttime inversion layer bathes it with warmer and drier air. So this area can experience the least amount of temperature swing between the highs and the nighttime lows because of a thermal belt. So unusual, instead of going down in temperature as you go higher, it goes up and then down. So that's a thermal belt. So knowing the location of thermal belts is important when you're fighting fire in the high country. Okay, winds in thermal belts are usually light and steady. So last slide, you need to pay attention to weather reports. You get updates on your mobile data terminal. There's always updates on the computer in the morning at the fire station. And firefighters are usually weather nuts. They like to watch the weather reports on TV. Some of them are better than others. But when you're out on a fire, there's two portable ways that you can get your weather around you, and that's a belt weather kit. You don't need to look up this YouTube or the next one. I've embedded them into our list of videos. And then the Kestrel weather meter. If we were in class, I'd pass one around. I have one here at home. They're great. They give you humidity, temperature, wind speed, and they're very accurate. They give you air pressure and barometric pressure and all of those kind of things. So that's it on air stability. Just the main things to remember is hot air rises, and yet when you go up in elevation, things get cooler. So as that hot air rises, it expands, it reaches its dew point, and it accumulates moisture, and you start to get cumulus clouds and then cumulus nimbus clouds, and that is a sign of unstable air. If you have a pyrocumulus formation over a fire, this is a really bad sign, and a lot of times the firefighters don't realize what's going on above them, and so they need that given to them in a weather report. But when you have a pyrocumulus-driven fire, like the station fire was, or the 30-mile fire, this increases fire behavior below by drawing in oxygen with upward convective motion and intense fire behavior. Okay, that's it on this one. We've got one last one about clouds and how they help us tell what's going on in the weather and in the sky around us. Okay, see you later.